Dear students, today I want to revise the topic thermodynamics. It purely depends upon three important laws of thermodynamics: Zeroth, first and second law of thermodynamics. At first, the Zeroth Law of Thermodynamics, it includes a very simple concept only: equilibrium. Here, the two systems in thermal equilibrium with the third system separately are also in thermal equilibrium with each other. That means, if the temperature of A and C systems are equal, B and C systems are equal, then we can say the temperature of A and B are equal. A good concept. Then, in order to know the first law of thermodynamics so neatly, we have to discuss the three important parameters: work, internal energy, and heat energy. At first one, the work, the simple concept, if a gas is enclosed in a system, and here it got a displacement dx because of the pressure exerted by the gas, and there we can say the power is that work is equal to F into dx. We know the force, that is nothing but equal to pressure into area, and there A into ds can be written as the volume. So the pressure into the change in volume, that is treated as the work. Here the two sign conventions, it is very, very important. Work done by the system is taken as positive. That is, the work done by the gas inside. That means the corresponding volume should increase. That is the concept. The work done on the system is taken as negative with respect to physics. And keep in mind, while work done on the system, its volume decreases. So the important two sign conventions. Look the graph. In order to find graphically the work done, see, look the curve here. The work done the thermodynamic system is nothing but equal to the area enclosed by the curve AB with respect to x-axis, the volume axis. Look the cyclic processes, and here it is clockwise. The work done is nothing but the shaded area, but we have to take a sign convention of plus. But here, an anti-clockwise concept, the area is nothing, the work done is nothing but the shaded area, but the direction is negative. Look, the very important sign conventions with respect to the cyclic processes. Very important. The clockwise as plus and anti-clockwise as negative. Look the next concept, the internal energy. It is defined as the total energy of the system due to the molecular motion and molecular configuration. And hence, we can represent as U is equal to UK plus UP. UK means the internal kinetic energy due to the motion. UP means the internal potential energy due to molecular configuration. Look the concept carefully. Ideal gas has only internal kinetic energy and no internal potential energy. But for real gases, got both the type of potential energies. When heat is supplied to a system, its temperature goes on increasing, and hence its internal energy increases. When heat is taken out of the system, its temperature and hence the internal energy decreases, hence negative. So carefully look the sign conventions. How the internal energy become positive and negative. The third term, the very important one, the heat energy. The energy that is exchanged between a system and its surroundings due to temperature difference is called heat. In a particular state, so temperature increment for a particular state, to say from 20 degrees Celsius to 80 degrees Celsius, amount of energy given to a water system can be expressed as mc delta T. But during a phase transfer, suppose the ice melt at 0 degrees Celsius, their dq is nothing but m into L. No, C is the specific heat capacity and L the latent heat. So keep in mind the sign conventions here. The heat absorbed by the system is taken as positive. The heat rejected by the system is taken as negative. So the very important sign conventions. In one word, we can say what is the first law of thermodynamics, the very important concept with the thermodynamics. You can write more problems based on that. Delta Q, the given amount of energy is utilized to increase the internal energy and for doing the work. So delta Q is equal to delta U plus delta W. That is the first law of thermodynamics. We can say it is based on the conservation of energy. Look, the thermodynamics processes. The first one, the isochoric process. Look, we can discuss different thermodynamic processes like isochoric, isothermal, adiabatic, isobaric, etc. Then what is the special condition for that? How the first law of thermodynamics changes? What is the corresponding equation of state? How much work is done? And what is the graphical difference between the pressure and the volume? So we have to discuss like that. So at first one, isochoric process. The volume remains constant. So the delta V, the change in volume becomes 0. If you just put for delta Q is equal to delta U plus delta W, and here the work done becomes 0, reason delta V becomes 0. Therefore, the first law of thermodynamics take the way delta Q equal to delta U. The equation of state, and keep in mind for isochoric process, if you just use P is equal to nRT, P by T is a constant. And here already said the work done is 0. And here the volume is a constant. So the curve is like this one, and we can say the slope is infinity. Look, the isothermal process. The temperature remains constant. Say the delta T is equal to 0. The change in temperature becomes 0. So there is no internal energy concept for ideal gases, and hence for first law of thermodynamics we can write delta Q is equal to delta W. The equation of state, temperature is constant, so PV is a constant. Look, the work done relations, the very, very important. We can write as nRT log V2 by V1. In terms of log to the base 10, we can say 2.303 nRT log to the base 10 V2 by V1 or P1 by V2. The very, very important concept. Looks the isotherm. The different curves. It's a very important entrance concept. Which one is greater? The T3 is greater than T2 is greater than T1. And we can think with a good concept. It's a slow process. The thermodynamic isothermal processes are slow process. And we can quote the best examples as melting, boiling, etc. Look, the another process, the isobaric process. And there we can say the pressure remains constant. Delta P is equal to 0. First law of thermodynamics changes to delta Q is equal to delta U plus delta W. Look the equation of state, and there the pressure is a constant, and hence we can say V by T is a constant. So simply the work done, take the formula as P into V2 minus V1. And here the pressure is constant, so the PV diagram is like that. The slope becomes 0, the tan theta becomes 0. Look for the adiabatic process, the very important concept for our entrance exam. You know that there is no exchange of heat. The delta Q should be equal to 0. Then for the first law of thermodynamics, we can write as a delta W should equal to minus delta U. Reason? Delta Q is equal to 0. Look, the three important relations for representing the equation of state of adiabatic process. PV raised to gamma is a constant. Then you can substitute PV is equal to nRT for different parameters. We can write as a TV raised to gamma 1, gamma minus 1 is a constant. Then P raised to 1 minus gamma into T raised to gamma is a constant. Look, the work done formula, very important. P1 V1 minus P2 V2 by gamma minus 1. Where gamma is the ratio of specific heats. Or we can write as PV, we can substitute it with nRT. So nR into T1 minus T2 by gamma minus 1. Look the slope, it is a very important for the PV diagram. It is minus gamma times P by V. So the adiabatic process. Then you should know the cyclic process. Look the graph, and you keep in mind it comes to the initial position, and hence the change in internal energy is 0. The first law of thermodynamics takes the simple formula as delta Q is equal to delta W. It's the very important concept. So these processes are very important regarding the entrance exams. And we can go through some very important previous year questions. A perfect gas goes from state A to B by absorbing 8 into 10 raised to 5 joules of heat and doing 6.5 into 10 raised to 5 joules of external work. It is now transferred between the same two states in another process in which it absorbs 10 raised to 5 joule of heat. Then in the second process, we have to certainly say the work is done on or by. So look, we know the first law of thermodynamics. The day can be written as a dq minus dw. We know here the dq is nothing but 8 into 10 raised to 5. And it done on external work, so 6.5 into 10 raised to 5. So we get as 1.5 into 10 raised to 5. The second process, the change in internal energy remains the same. So dW is equal to dq minus du. So 1 into 10 raised to 5 minus 1.5 into 10 raised to 5. So you get the value minus 0.5 into 10 raised to 5 joule. So because of minus sign, we can say the work done on the gas. Work done on the gas. Look the next question. In a thermodynamic process, pressure of a fixed mass of a gas changed in such a manner that the gas molecules gives out 30 joule of heat. Once again, in a thermodynamic process, the pressure of a fixed mass of a gas is changed in such a manner that the gas molecule gives out 30 joule of heat and 10 joule of work done on the gas. If the initial internal energy of the gas is 40 joule, then the final internal energy will be, look the steps. We know the concept from the question. dq minus 30 joule, dw the minus 10 j. Apply the proper sign conventions. The initial internal energy is 40 joule. You know dq is equal to du plus dw. The change in internal energy can be write as UF minus 40. So you get the answer. A good concept. Look the graphical question. An ideal monatomic gas is taken around the cycle A, B, C, D, A as shown in the PV diagram. The work done during the cycle is given by, look the graph, the simple. The work done is the area enclosed. That is a very important concept. It is cyclic also and hence it is positive. So you can just use the area of a rectangle, length into breadth. So AD into CD. So AD is what? The volume. So 2P minus V into 2P minus P. So you get the answer as a PV. Look the another question. When an ideal gas in a cylinder was compressed isothermally by a piston, the work done on the gas was found to be 1.5 into 10 raised to 4 joule during the process about. So the heat is flowed out from the gas or into the gas, we have to find. So in isothermal expansion, there is always an increase of heat which must flow out of the gas. So that is a very important concept. So loss into the system. You know delta Q should be equal to delta W. So it is in joule. So have to convert it into calorie by dividing it to 4.18. So you get the value as minus 3.6 into 10 raised to 3 calorie. A good question. A monoatomic gas is suddenly compressed to 1/8 of its initial value adiabatically. The ratio of its final pressure to the initial pressure is given. The ratio of the specific heat of the gases is 5/3. You know the adiabatic process, and here we have to relate between the pressure and volume. So P1 by P2 is V2 by V1 the whole raised to gamma. So that V2 by V1 is given as 1/8. So the whole raised to 5/3. So you get the answer as P2 as 32 times P1. Look another good question. At 27 degrees Celsius, a motor car tire has a pressure of 2 atmosphere. The temperature at which the tire suddenly bursts will be gamma. Here it is given as 1.4. If it is a quick process, we can say it is an adiabatic process. So here we have to link between the pressure and temperature. A good equation, keep in mind, P raised to 1 minus gamma into T raised to gamma is a constant. So you can just properly substitute, you get the answer as 246.1 Kelvin, and is valid for our Kelvin scale, this relation. It is very important. The next, our second law of thermodynamics, the very important concept. One question we can wait from this area. The second law of thermodynamics. We have to get the principle of heat engine and the refrigerator, and hence that the second law of thermodynamics are expressed in two forms. The first one, the Kelvin Statement. Carefully you must read it. It is impossible to get continuous supply of work by cooling a body to a temperature lower than that of its surroundings. But the Clausius statement, the same concept in another form, it is impossible for a self-acting machine unaided by an external agency to transfer heat from one body at a lower temperature to another body at a higher temperature. So we have to go with the heat engine, and keep in mind a heat engine is a device which converts heat energy into mechanical energy, and is with the three important parts. A source, and keep in mind it is at higher temperature, the working substance, and the second one is the sink. Keep in mind it is at a lower temperature. And look, the working substance take the QH amount of energy from the source, and after doing W amount of work, the rest is given to the sink at temperature QL. The corresponding temperature of the source we can write as TH, the sink as TL. Then the efficiency of the heat engine is simple, the work done per cycle by the total amount of heat absorbed. That is the first one from the source. So the work done is nothing but the change in QH minus QL by QH. So this is a very important relation, the efficiency of a heat engine. And here TH and TL are the temperature of the source and the sink. Look, the refrigerator principle. A refrigerator or a heat pump is basically a heat engine which runs in a reverse direction of heat engine process. We need the working substance to take the QL heat from a body at lower temperature, has a net amount of work W on it by an external agent, and it gives out a larger amount of heat QH to a hot body at a temperature TH. And is a very important concept. They just look the flow diagram. The working substance, by doing W amount of work, that take the amount of energy from the sink and is given to the source. Normally the source is the outside of the fridge, we can say. The very important concept, the coefficient of performance beta. And keep in mind the heat extracted by the work done. QL by QH minus QL. Look, the very important formula as a T2 by T1 minus T2. A theoretical concept with 100% of efficiency. That is the Carnot's heat engine. Look the four important parts: the source, the sink, working substance, and the non-conducting platform. The very important concept, the Carnot cycle, the four important processes in order: isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. It's a cyclic process. The total internal energy becomes zero. And keep in mind the efficiency as 1 minus T2 by T1. By this relation, the efficiency depends only on the source and the sink temperature and not on the nature of the working substance. Okay, with a good question. The efficiency of an ideal heat engine working between the freezing point and the boiling point of water is, we know the simple relation as 1 minus T2 by T1. The T2 is the sink temperature, the T1 is the source temperature, but we have to express it in Kelvin. You get the answer as the 26.8%. Another two questions are waiting. A refrigerator extracts heat from water at 0 degrees Celsius and rejects it to the room at 24.4 degrees Celsius. The work required by the refrigerator for every 1 kilogram of water converted into ice is, you have to take the latent heat of ice as 336 kilojoule per kilogram. So the total heat produced per kilogram, it is M into L, so roughly 1 into 336 kilojoule. But we know as Q1 by Q2 is equal to T1 by T2, we get the value of Q1. So the work is nothing but Q1 minus Q2. So simply 366 minus. So you get the answer as 30 kilojoule. A good question, a previous year question. A simple question is waiting. The Carnot engine cannot give 100% efficiency because we cannot. Actually, the Carnot engine is a theoretical concept. Can give the 100% efficiency only when, yes, that is very important. Absolute zero temperature should be reached. It is not possible, and hence not with the 100% of efficiency. So, the students, you must give importance to the three chapters: heat, thermodynamics, and kinetic theory of gases. if you just go through the last previous year question papers, the more questions are coming from these three areas. So you must try to do maximum MCQs. It will get maximum rank. God bless you. Take care.